Hello guys, nice to see you. So last week we discussed the topic related to ray optics, and hello. So last week we discussed the topic ray optics, and in particular we focused on introduction of nature of light, dual nature of light. Then we had topics which covered formation of image formation in by reflection and refraction. So based on the laws of introduced laws of refraction and reflection, and there were formation of image by flat mirror and spherical mirrors, and also by refraction when we have some interface between transparent mediums with different optical properties, for instance, different index of refraction. And based on that model for forming image by refraction, we introduced the concept of thin lens and derived equations which describe image formation in thin lenses. Actually, lens is represented by two curvatures with the same or different radius. It will be like first and second surfaces of the lens, and some refractive index of refraction, which is the property of the material from which this lens was made. So today we switch to another topic, and we'll discuss a bit different features of light, and in particular this will be wave optics. So what does it mean? So we will focus here on the wave nature and properties of electromagnetic waves, which are in the visible spectral range. However, so this is relevant for light by definition, but the concepts which we are going to discuss here, they are also valid for other frequencies like wavelengths of electromagnetic waves, and also mechanical waves, because we will start first to discuss the interference effects, like Jung's experiment with like double-slit experiment, famous, so which very convincingly shows the wave nature of light, and these concepts of interference, like superposition of two coherent waves. This is also true for mechanical waves, for instance, which have a completely different nature from electromagnetic waves. But the basement of the effect is actually common for any type of waves. Okay, so let me switch the camera, and I will share my screen. 1 second. Okay, so when we have superposition of two waves, as we know from study of mechanical waves, we may observe some constructive or destructive interference. So let us focus on this image here on this slide, and this is the representation of double-slit experiment. So what do we have here? We have some plain electromagnetic wave. Then we have two very small slits at certain distance from each other. So we remember that according to ray optics, assuming that the diameter of the slit is much larger than the wavelength of light, then light will just go through it without any additional effects. However, if this slit gets very small, because of diffraction, these two slits could be considered as sources of, like point sources of electromagnetic waves of the same frequency. Since they are located at this plane parallel to the wave front of the plane electromagnetic wave, all this electromagnetic wave hits the both slits at the same moment, and that's why these slits, they are considered as sources of coherent electromagnetic waves. And what does mean coherent? That is very important in order to see and observe and measure interference effects. Means that the phase shift between these two sources is constant over time, so it doesn't change. So we can have 2-point light sources if they are not coherent, if the phase shift between the electromagnetic waves which they irradiate will be changing over time. So we will deal with some instantaneous interference pattern, which will change very rapidly, and it will be impossible to detect any pattern because it will be continuously changing. So in order to get some steady state interference pattern, we need to have two coherent light sources. And that could be realized nowadays with lasers because of their features. You can control phase and wavelengths. However, in this experiment, double-slit Young's experiment was carried out in 1801, so definitely there were no lasers, and this is very simple but reliable way to create two sources of coherent electromagnetic waves. So another requirement is monochromatic light, because you will see later when we discuss quantitatively this effect that wavelength is an important, like, essential parameter which will define position of this maximum and minimum. So in order to have clear, like dark and bright fringes as the result of interference effect, we need to have at least close to monochromatic illumination. Means this plane electromagnetic wave which hits the slits, and that should be a monochromatic light. So that could be realized with adding certain optical filters which will block different, let's say, which it either some band pass filter which will block all wavelengths, but in the narrow wavelength region, it will let light to pass through, and that could be considered as, in some approximation, as monochromatic light. So what happens here? We have, as I mentioned, these two slits which work as coherent light sources and of monochromatic wavelengths. And then we have either, as I mentioned at the beginning, constructive or destructive interference. So means when we have interference of two electromagnetic waves, when they come in the same point in phase, so we have so-called constructive, the amplitude of the resulting electromagnetic wave, which is superposition of two sources, will be larger than amplitude of either of these electromagnetic waves. Or when they come in some point at like in the opposite phases, then we will have minimum brightness exposed on this screen, and that will correspond to destructive interference when the amplitude of the resulting signal at this point will be smaller than the maximum amplitude of one of initial waves. So it really depends. It could be zero if amplitudes are equal of these electromagnetic waves which undergo interference. Then they can compensate each other completely, and then like amplitude of the resulting signal will be zero. But depends on which intensity. We remember that intensity of electromagnetic wave is proportional to the amplitude value of x square of amplitude value of the electric field. So then we will have a situation when we cannot compensate completely because one wave is more intense than another. So there could be different combinations. So here is another illustration of this in phase and out of phase conditions when we see bright and dark fringes. So if these two waves originated from two slits come with like in phase to some point, it's either point O or this some random point P, which correspond to some order of interference. If they come in phase, they kind of enhance each other, and we see some bright fringes. If they come in the opposite phase, they compensate each other, and we have dark fringes. So what is the reason for this effect? Like why at some points they come in phase, at some points they come in opposite phases? So that originates from the difference in path for electromagnetic waves from both of the slits towards certain point where we want to check what situation will be realized. So for instance, here we have two slits at the distance d from each other, and at distance L we have the screen. So here is some y coordinate, this position of the point P. So we have two options. We can define this position of point P in the like angular way with this angle theta. So these two angles are the same. And we can also define it as like linearly in the system of coordinate by this coordinate y along this line, the cross section of this screen. So what do we see here? We have R1 and R2. Those are passes which electromagnetic waves originated at these two slits need to go, like travel through in order to reach point P. And just from this simple geometry, you see that there is certain delta, which is defined as d distance between the slits, and sine times sinus theta, this angle, which in its order defines angular position of point P. This delta is the difference in path, and this difference in path will define either we have constructive or destructive interference. So let us go now to this slide where we can write. So we can write down these conditions for constructive and destructive interference. So we remember that we have this delta, which is equal to d times sinus, not alpha, that's theta, and this is difference in path. So the condition for constructive interference is either when this delta is equal to 0, so it's so-called first order interference, like maximum. We will mention this, or if this delta is equal to some integer multiple of the wavelengths which we deal with, so that waves are originated from two slits, coming to this point P in phase. So in this case, we can write for interference maxima position, angular position, and write that d times sinus theta is equal to m times lambda, where m is equal to 0, plus minus 1, plus minus 2, and so on. So this m is called the order number, and the central bright fringe, which corresponds to theta equals to 0. This interference maximum is called zeroth order maximum, and so on. We have first order maximum, second order maximum, third order maximum, depends on the value of this order number. Now let us define the condition for destructive interference when wavelengths come in opposite phases. So in that case, delta is an odd multiple of half of wavelengths, lambda divided by 2, and under this condition, this wavelength will come in the opposite phases. So it will be d times sinus theta. So it means that this difference in the path of both waves from the slits toward the point P should be an odd multiple of lambda divided by 2 in order to get destructive interference. So it will be m plus lambda, no, sorry, it will be like 1 over 1/2. So it will be m plus 1/2 times lambda. So that means that m will here also change in the same range as it was changing for the first case, but here we add 1/2, and that's why we always have this odd multiple of lambda divided by 2, which can fit into this difference in path of two waves. So now we also mentioned previously about an option to represent linear position of the fringes, and that in order to do that we can introduce tangent theta, and that will be equal to y divided by L. So y is the coordinate position of the point P, and L is the distance from the slits to the screen where we project this interference picture. So from here, we can write that y bright is like for maximum of interference, will be L times tangent theta bright, then y dark will be L times tangent theta dark. So these bright and dark, they will be, these thetas, they will be defined by these equations. And assuming the case when we have small angles, theta, we can write that tangent theta is close to sinus theta, and our equations can be for linear position of fringes can be rewritten in the following form. So it will be y bright equals to L times, instead of tangent we put sinus, sinus theta bright, and that, as we remember, is equal to L times m times lambda divided by d, where d is distance between the slits. So the same we can write for the dark fringes. Y d is equal to L times sinus theta dark, and this is equal, according to the definition of minima of interference, L times m plus 1/2 times lambda divided by d. Okay, so now we have already explained the reason for the changing bright and dark fringes as a result of interference of these wavelengths originated from two slits which act as sources of coherent light, and quantitatively describe the angular and linear position of these bright and dark fringes on a screen, which is located at certain given distance from the slits. So at this point, like so far, we're discussing only on positions of bright and dark fringes, but we didn't discuss the distribution of light intensity along the screen. So we just claimed that, okay, this is bright, this is dark. However, these equations which we derived, they give us information about the position of the center of bright and dark fringes. But if we take a closer look, for instance, here, we see that it's not just uniform intensity bright and uniform intensity dark fringe. It's rather some gradient from dark to bright and then from bright back to dark. So definitely there is some distribution of light intensity, and again, these equations which we introduced here, they define only the position of the center of these fringes. But now, after we define this position of the center of the fringes, we want to understand a bit more how light intensity is distributed along the screen. So in order to do that, let us consider two waves with the same frequency, like angular frequency. The constant phase difference and the same amplitude, E naught. So we can write that for first wave, we have E naught times sinus omega t. For the second one, we have E2 equals to E naught times sinus omega t plus phi. And this phi is the phase difference. So just to remind, this delta is difference in the path between of two waves, is equal to d times sinus theta. And if this delta is equal to 1 lambda, like if delta is equal to the wavelength, then P is equal to 2 pi radians. So what does it mean? If delta is equal exactly to 1 wavelength, then it just doesn't cause, so we will have constructive interference, and the phase shift is equal to 2 pi. It's kind of one cycle lagging behind because of this path difference. But they will come in the point of observation in phase. But from this relationship, we can, in other words, claim that the phase difference of delta is the same fraction of lambda of the wavelengths as the phase difference phi is of 2 pi. So mathematically, we can write delta over lambda is equal to phi over 2 pi. From here, we can write the expression for phi in terms of phase difference, 2 pi over lambda times delta. And we know that delta is d times sinus theta. So it will be 2 pi over lambda times d times sinus theta. Okay, so this is the expression for the phase difference in our case between the two waves. And let us go to another slide. We can write the resultant signal, which is formed because of superposition of two waves. So let's call it E. It's equal to E1 plus E2. And this is E naught. They have the same amplitude. We can factor this out from of parentheses. That will be sinus omega t plus sinus omega t plus phi. So now we can use the following trigonometric identity in order to proceed further. So if we have sinus of A plus sinus of B, that could be represented as 2 times sinus A plus B over 2 times cosinus A minus B over 2. So taking this into account and considering that A in our case is equal to omega t plus B and B is equal to just omega t, we will get the expression for the resultant time varying electromagnetic wave as result of interference, like superposition of two waves, E1 and E2. So that will be 2 times E naught times cosinus phi over 2 times sinus omega t plus phi over 2. So here we see that amplitude of this resultant signal, like wave, will be given by this equation. So it will be 2E naught times cosinus phi divided by 2. So if phi is equal to 0, 2 pi, 4 pi, and so on, the amplitude of the resultant interference signal will be 2 times E naught. So it means that we will just have in phase condition, constructive interference, and 2 amplitudes will just add up, and we will get twice higher intensity, like amplitude of the signal, not intensity. So if phase shift is equal to pi, 3 pi, 5 pi, and so on, then we will get 0, which will correspond to the destructive interference when 2 equal in amplitude signals will just compensate each other. So now we know that light intensity, so our goal was to understand how light intensity is distributed along the screen, like in between this bright and dark, in between the centers of bright and dark fringes. So light intensity, I, is proportional to the square of electric field in electromagnetic wave, which is the result of interference. And that will be based on the previous equation, which we derived for E. It will be 4 times E naught square times cosinus square phi over 2 times sinus square omega t plus phi over 2. So it is necessary to understand that when we deal with intensity, there should be some option to measure the light intensity, which is taken as some average over one cycle, like one period, or multiple periods. So it's some average over some time period. That's how most instruments measure light intensity. So then, in order to get to this average intensity, we need to get average over one or more cycles for this sinus square of omega t plus phi divided by 2. And we have shown previously that average over one cycle or more for such function is actually equal to 1/2. So maybe we can write something like this: sinus square omega t plus phi divided by 2 average over one cycle will be equal to 1/2. So in this case, we can represent our light intensity with distribution in the following way. So it will be, so far it's not yet distribution in along the, let's say in the angular or linear forms, but we will come to this now. So I is equal to I maximum times cosinus square of phi over 2. So I maximum stands for the maximum intensity of on the screen, like in the center of the bright fringes. And now if we substitute instead of phi its expression which we derived in the previous slide, that was 2 pi over lambda times d times sinus theta, we will get this will be already angular position distribution of light intensity. I maximum times cosinus square. Instead of phi, we have this expression. Keep in mind that we have 2 in the denominator. So we end up with pi times d times sinus theta divided by lambda. So we see that light intensity with this sinus theta, like angular position, changes as cosinus square. So it doesn't go to negative values because it's cosinus in second power, which makes sense because light intensity cannot be negative. But it goes from some maximum to the minimum, like which is defined by this function periodically. So if we want to make a transition to the linear position of this distribution of light intensity in terms of y coordinate, then we need to take into account that sinus theta for small angles is equal to y over L, as we discussed earlier. Y is y position along the linear coordinate along the screen, and L is the distance from the slit to the screen. Then taking this into account, we can write I intensity distribution like as a function of linear coordinate y, and that will be I maximum times cosinus square of pi times d divided by lambda times L, and this everything times y. So this is the equation which defines the distribution of light intensity in the linear coordinates along the screen when we have 2 slit interference. So let me share the screen in order to show graphically like how it looks. Here it is. So if we have 2 slits, we have this distribution of light intensity. As you see, we don't have just some step square profile like bright, and here like dark, and then again bright. So we have kind of gradient between dark and bright, and then again from bright to dark. So that's how it looks here, and this is the distribution which is described by equation which so it's light intensity versus d times sinus theta. So it's in terms of angular position. We see this minimum and maximum of light intensity. So if we increase number of slits, so far we were talking only about 2 slits, but there could be many of them. So if we go for instance, for 3 slits, then for more than 2 slits, the pattern of light intensity distribution contains a primary and secondary maximum. So what does it mean? We have primary, like most distinct intense maximum, and here in where should be minimum, there is some secondary maximum, which is much weaker than primary maximum, but we get this pattern here. And if we go further with the increase of number of slits, means we increase number of coherent light sources. We get more and more of this secondary maximum, which will be, their number will be equal to n number of slits minus 2. However, it should be mentioned that with the increase of number of slits, the maximum, the primary maximum increases in intensity, and secondary maximum, they decrease in intensity. So we get more of them, but their intensities get weaker. So when we go to some sufficiently large number of slits, for instance, here is shown for 10, we get very sharp and intense maximum, and very many and weak secondary maximum. So primary maxima increases in intensity and gets sharper, and secondary maxima just get weaker, and we get more of them. So we have more sharply distributed bright and dark fringes. There is no gradient anymore, almost, between going from dark and light. We have just very sharp line of sharp bright fringe, and then there is also very sharp but very broad here, but well-defined dark fringe. So, however, keep in mind that light intensity here is still not equal to 0, because it corresponds to this maximum of to the level of secondary maximum, and they are much weaker than primary maximum. However, they are still not 0, so we still get some signal in this area. So this is pretty much everything what I wanted to tell you during this lecture. We introduced the Jung's 2-slit experiment, explained why we get constructive and destructive interference, so why we have periodic bright and dark fringes on the screen, quantitatively describe the condition for the position, angular and linear position of these dark and centers of dark and bright fringes. And in addition, we quantified the derived equation for the angular and linear distribution of light intensity along the screen where the interference pattern is projected, and discuss how this light intensity distribution will change if we have more than 2 slits, so multiple slits interference cases. So the main message from this part is that with more than 2 slits, we deal already with primary and secondary maxima, and in the on the way of increasing number of slits, the primary maximum gets sharper and brighter, and we get more but weaker secondary maxima in between. So thank you very much for attention. Take care, have a good evening, and see you on Wednesday when we will continue discussing wave optics. In particular, will be interference because of reflection and refraction effects in some thin films and so on. Okay, thank you for attention. Bye-bye.